Hi, in this video I'm going to go through an example that uses reinforcement learning to control the steering and acceleration of a car to keep the car in the driving lane and keep a safe distance with the next car in front, respectively. In the last video I showed how to use a DQN agent to control the steering and keep the car in the lane, and in this video I'm going to train that agent and another agent at the same time for the acceleration and keep it in the same distance using a DDPG agent, Deep Deterministic Policy Gradient Agent. Okay, let's go to the example. This is the example that I'm gonna use, which is in the description. The link is in the description of the video, and to run it, just copy the command and then do Ctrl V in the MATLAB session. In the MATLAB session, hit Ctrl V. You have the command in the buffer. Oops. Okay, going back here, it has to appear. I copy. Now I have the confirmation, so I can come back in here and hit Ctrl V. Okay, there you go, and that will open it. I already had it open, but that's how you open them all. And okay, so now let's first load the parameters into a base workspace, which are similar to the last example, but some additional parameters. We have the mass, the distance of the wheels, the stiffness, from the front and rear tires. The tau is for the longitudinal time constant that is used in the computation of the forward motion. And we also have the starting position, the initial velocity and initial position of both the vehicle in front and the vehicle that you're controlling. So we have to model both vehicles. And also we have the default distance for the safe distance and the time gap, which is used in the computation of the distance. The V set is the desirable velocity. Once you are at a safe distance from the front vehicle, you want to be at 28 meters per second. And also you have the bounds of the acceleration. For the acceleration, you go from -3 to 2 meters by square second. So it's going to be a continuous, so the acceleration is going to be a continuous domain for the action, while the steering, we keep it as a discrete domain. So we have radians. The steering is going to go from -0.5 radians to positive 0.5, but since we're going to use a DQN for the steering, it has to have a discrete domain, so we divide that domain by 32 chunks, 32 elements, so that's how we make it discrete. But in the case for the acceleration, we're going to use a DDPG agent, which can work with continuous acceleration domains, so we keep it continuous. The rho is for the curvature, and this is the initial lateral deviation and the initial angle error. So this is the same as the previous video. For that video that I'm referring to, I'm gonna put it into the description, the link into the description of the video, which is basically controlling the steering with just a DQN network. Okay, so now let's run the command, and you notice that in base workspace we don't have anything, but now we have all those values. Okay, so now let's load the model. And let's give a quick overview of the contents of the model. The model is gonna model the dynamics of the car, of the vehicle, and also it's gonna do some processing to feed the reinforcement learning agents. And you can see that we have a couple of reinforcement learning agents. The top one is for acceleration, and the bottom one is for steering. And both of them are in red because we have not created them yet. And notice that the inputs are as usual. You have the observation, the reward, and the signal that the episode is over. And the action, the output action, is going to be clamped because the agent can indicate an action that is out of bounds. So to make sure of that, we have a saturation block. And then you can see that the top action is going to be acceleration, and the bottom action is going to be the steering. That's going to change the dynamics of the vehicle, of the ego vehicle, the vehicle in control. And then we get the observations, the reward, and it's done from this subsystem. So in here, the simulation, the environment is done through Simulink, which is very convenient for reinforcement learning. And the environment consists of these two blocks and the physics part. And also for the environment, you have to indicate which are the agents. Okay, so let's go to the dynamics. So the input in the previous example, the longitudinal velocity was constant, so that was a constant. So now it's a little bit more complicated because instead of having a constant velocity, you have an acceleration. So we have to model the dynamics of the vehicle in front, which is the lead vehicle, which has an initial position and initial velocity. And we want to make the life hard for the reinforcement learning agents. So for the lead vehicle, you're gonna see in a moment. Okay, it froze. It's gonna come back in a minute. Okay, finally open. So to make the life hard for the reinforcement learning agent, the lead vehicle, the vehicle in front, is gonna have an acceleration of a sine wave that is gonna accelerate, deaccelerate, accelerate, deaccelerate, and then that acceleration is integrated and change a little bit of phase, and basically you add it to the initial velocity to get the longitudinal velocity of the lead vehicle. Then you integrate that and you have the position, and then you add it to the initial position and you have the position of the car. Pretty straightforward. Okay, for the ego vehicle it's more complicated because it has an acceleration coming from, and also a steering angle coming from the agents. So, and you have an initial position as well. And in this case, let's go inside of here. This is the mole. So we have dynamics similar to the previous mole that we saw in the last video. You have the angular acceleration, and as in the Newton force equation, you have force equal to mass multiplied by acceleration. So if you want to have the acceleration, you have to divide force by mass. So that's why the mass is divided in here, and you have the force computed by these coefficients, and basically the input acceleration. So basically you're getting the acceleration in the end from here, and when you integrate the acceleration, you're gonna have the velocity, and that's for the longitudinal, the lateral velocity. So you have the longitudinal velocity and the lateral velocity. So they basically, depending on the angle is gonna determine the two of them. So you have the steering angle, and you have to compute it. In here you have the angle. So that one is gonna determine, it's gonna affect the longitudinal velocity. And also it affects the lateral velocity, as you can see in here. It affects both of them. For the case of the angular acceleration, you have to, instead of dividing by the mass, you have to divide it by the moment of inertia, and then you integrate and get the velocity of the angle. So now you have the three values that we need in terms of velocity: angle of change, lateral velocity, and longitudinal velocity. And you integrate the longitudinal velocity to get the position of the car, and you add it to the initial position. Now we have the position and velocity. That's all that we need. But in addition to that, we have to compute additional data for the observation. So we go to the ego sensor, and the ego sensor takes the initial relative yaw angle and the initial lateral deviation, which is called E1 and E2. Those are the observations for the steering agent. And of course you need the raw curvature to make the computation. So from here we already have the longitudinal velocity and also the yaw rate, the rate of change of the angle. So now we want to get the lateral deviation and the relative yaw angle, and both of them affect each other. So in here we're going to compute the rate of change, the actual relative error, a rate of the angle, a relative change of the angle, and that is computed through the curvature, longitudinal velocity. They subtract each other, and you get that relative speed of the angle change. Then you integrate that and have the initial relative yaw angle error, and then you get the relative yaw angle error. So that goes for these two are go to observation. So this is E2 and this is E2 dot, the derivative of E2. Yeah, so basically for the longitudinal velocity, you similarly take the velocity multiplied by the longitudinal velocity, multiply the yaw angle rate, No, this is the actual yaw angle. This is integrated already, so it's the angle itself. So you multiply the angle by this one, and then add the lateral velocity, and there you have the rate of change of lateral deviation. So you integrate that, and you have the actual lateral deviation, the position-wise. Okay. So now we have the rate of change of E1, E2. This is for the steering. It is the same as the previous video. And for the lead vehicle, we have to do some additional pre-processing. And you can see in here, I think we already saw this. Okay, so we have all the values that we have that we need for the observation. Now we go to additional pre-processing to compute the reward for the agents and the actual observation, that which require additional pre-processing. And you can see that the actions are fed back into this block, to this subsystem, because we want to include the steering and the acceleration in the reward function. So let's go quickly to this one. We saw already this one. We have already from the dynamics, we have the derivative of E1 and E2, and we have E1 and E2. They are fed directly. So in addition to that, we need the integrals of the positions. So we have the integrals of the accumulation of the positions, and we have the derivatives of the E1 and E2. So that's we have a total of 6 observations for steering. Okay, that's a lateral deviation, yaw angle, the yaw angle error, the angle error, and their derivatives and integrals. Okay, so for steering, now we're gonna compute the reward, and the game is gonna be over when you get out of the lane, and that's gonna happen when your lateral deviation goes above 1. The absolute value goes above 1. So you're gonna get a big penalty for that. You can see the penalty is negative. So in here we have a block to turn whatever comes from here to negative. So anything that is positive in here is a penalty, and anything that is negative is gonna be a reward. Okay, so let's take a look at that. So this is negative, the first one. So this is gonna be a reward, and the reward is gonna happen when the lateral deviation is almost 0. So that means that your car is in the lane. So you get somewhat reward, and not as big as the penalty that you get for getting out of the lane. And so you get a reward for that. And for the higher the lateral deviation, you get a small penalty. So you get as you are deviating from the lane, you continuously increase the penalty until you get out of the lane, and you get a even worse penalty. And of course, you want to put a penalty on the action. The bigger the action, the worse the agent is behaving. So you can imagine that when you're in the highway and you're trying to move the steering wheel, the more you move it, it means that you're out of control. You want to move it a little or nothing, and it means that you're in control. So that's another penalty that you get if you move too much the steering wheel. Okay, so that's for the rewards, and the is done signal, reward, and observation for steering. Let's go for the acceleration, which is the new agent that we have in here. For this one, we first need to compute the safe distance. And to compute the safe distance, we have to go from the velocity of the ego vehicle, and that's it comes from the velocity of the vehicle that you're controlling, because as some driving exams indicate that driving classes indicate that when you're driving in the highway, your car must be 1 car per 10 miles per hour of distance from the car in the front. So for example, if you are at 10 miles per hour, you must keep 1 car of distance. But if you are at 70 miles per hour, there should be 7 cars in front. 7 cars, it should be the gap between the car, between your car and the car in the front. So basically the distance is proportional to the velocity of your car. So the bigger the velocity, the bigger the distance. And that's why the velocity of your car is multiplied by the time gap. And that's gonna get you a distance plus a default distance, and that's how you compute the safe distance. Okay, so now with the distance, you're gonna get the error. So you're gonna subtract the distance, the relative distance between the car in the front and your car, and that's gonna give you the error, and that's gonna be one of the signals. Not directly, you're gonna see why. So we're gonna the velocity is one of the observations data that goes directly to observation vector. For this agent, you're gonna get 3 observation points. So you get the error of the velocity between the ego car and the car in the front, and you integrate that to get something similar to a relative distance. Okay, and then you get the velocity of the lead vehicle, the velocity of the ego vehicle, and then what's gonna happen here is that if the velocity of the lead car is smaller than the velocity that you want to go, which is 28 miles per second, then you're going to take the velocity of the lead car. And the rationale for that is that if the vehicle in the front is too slow, you want to go as slow as that vehicle because you don't want to hit it. But if the vehicle is above the velocity that you're setting, then you go with the velocity that you want. You're going to see that in the simulation later. So then after you get the velocity of reference, that is the velocity that you want to go, then you subtract it from the velocity that of your vehicle. So you want to bring the velocity of the ego vehicle to this velocity reference, so you want to bring this to 0. So that's gonna go into a reward. So you can see it in here, a velocity error and the accelerator. Those are gonna go into a reward. So this is computing the reward. Again, the whatever positive is here is gonna turn negative because of this block. And then also the relative distance from your distance, if it is you're gonna see the computation here. If the relative distance is less than 0, it means you crash your vehicle, or you could have crashed it, so you're gonna end the episode. The episode ends there. But in addition to that, you have to stop it if the car stops, because the agent can say, okay, if I don't want to crash the vehicle in front, I just gonna stop. If I don't want to get out of the lane, I just gonna stop. So to avoid the agent doing that strategy, then you stop it when the car stops to indicate that it is bad. So if the episode stops, then you give a negative 10 penalty, which is the biggest penalty that you can get. And okay, now going back to the error velocity, which is the difference between the velocity that we want to be and the actual velocity of the car. It is fed to the reward, and that you're gonna get a penalty. The higher it is the error, the higher the penalty. So the agent will want to bring that error to 0, and by bringing it to 0, you bring the velocity of the ego car to the velocity that you want to go in, which is either 28 miles per second or the velocity of the front vehicle, one of the two. Okay, so again, similar to the steering, you want to give a penalty. So anything that is positive here is going to be a negative penalty because of this block. So you want to give a penalty for the acceleration. It's similar to when you go in the highway, you want to go at a constant acceleration. So if you accelerate, it means that you're out of control and it's can be dangerous behavior. So that's what you want to penalize for too many acceleration or the acceleration. Okay, so you want to give also a reward. This negative becomes positive. So this is a reward. These two are penalty and this is a reward. So if the velocity error is less than 1, it means that you are in control. I mean, you're at a safe distance. Then give a very good reward, which is higher than this penalty. Okay, so you're gonna accumulate rewards as you keep the car at the right place, at the right velocity, at the right distance. Okay, so that's your reward, your signal to end, and your 3 points of observation, which is the velocity error, the distance error, and also the velocity of the ego car. So with that, we have everything that we need to train these agents. So now let's create the reinforcement learning agents. So let's go back to the MATLAB session, and okay, for the again, as I mentioned, the acceleration agent is going to have 3 observation inputs, so that's why this is the size. The observation in both agents are going to be contiguous, and they don't have limits, negative infinity to infinity. And for the acceleration, it's going to be continuous. So we use the same function, RL numeric spec, to create the information for the action. It's the same one for the observation because both of them are continuous, but this one has lower limit of negative 3 meters per square second to positive 2 meters per square second. So that's the limits of the acceleration. For the case of the steering, we already know that we have the lateral deviation, angle, and their corresponding derivatives and integrals. So we have a total of 6 observations, and none of them has limits. So for the action, instead of using RL numeric spec, we're going to use RL finite spec, set spec, because we're going to use again a DQ agent, which is limited to discrete actions. So we had to create a discrete set of actions. In this case, we're going to go from negative 15 degrees to positive 15 degrees. So we divided, and basically we create a total of 31 possible actions. So that's how we discretize the actions for the steering agent. And now we're going to train a couple of agents at the same time. So you're going to see a lot of pairs, and they always have to go in the first order. First agent always goes first, second agent always goes second. So we can see that in here. So we have a couple of observations. One for the first agent, second agent. The same goes for the actions also. You'll see in a moment how we're going to use that. Also, when we create the environment, you can see that we pass the observation info, which comes in a pair, the action info for the 2 agents, which comes in a pair, and also the blocks. The blocks are the string path for the 2 blocks in the Simulink model. So you can see this is the name of the model, and this is the name of the block where the agent is. Both those are the 2 agents, and you can see those are the names that you get in here for the agents. So now we have the name of the agents and the observations and their actions, and the model. This is just the name of the Simulink model. And with that, we create the reinforcement learning environment using Simulink. Very easy. For reset function, it's basically a lambda function that is going to initialize the position of the lead card, and also the initial lateral deviation and the initial yaw angle, relative yaw angle. So basically, we get these are the values that we want to control. That we want to put the car at a safe distance and the car aligned in the lane. So by randomly putting these different scenarios, we get different types of training for each episode during the training. Okay. So now we have the reset function. We're gonna use this RNG function to make this example reproducible. Repeatable. We're gonna use a sample time of 0.1 seconds. Now we're gonna create the DDPG agent for the acceleration, and then the DQN agent. So before going into details of how to create it, I'm gonna give a brief background of the DDPG agent. I'm not gonna do it for the DQN agent because I already did in the last video. So here's the page describing the DDPG agent, the deep deterministic policy gradient. And I'm gonna put this link into the description of this video. And it's an agent that has an actor and a critic. It has a Q value function to predict the expected long-term reward, and uses RL Q value function to create it. And also for the discrete the actor is gonna be deterministic using this RL continuous deterministic actor. So we have it is deterministic and continuous as well. Okay, so one of the properties that this agent has, as other agents have as well, is that it collects an experience buffer, and from that experience buffer it is randomly selected to have a good statistical properties. You get a mini batch, and both of them can be configured, and basically it's going to train the critic to minimize the error of the long-term reward, and it's going to train the actor to maximize the actions that take rewards. The reward taken by the actions. And similar to the DQN, you're going to have a pair for each actor and critic. You notice that this is the parameters for the neural network of the actor, and these are the parameters for the critic. And notice that there are two actors. and two critics. The target is updated based on the values of the other. So this is updated. The parameters of this one are updated based on the values of this one at certain cadence. But the actual trained networks are these. But these ones are used to compute the reward, and you can see it in a moment. Okay, so here's the function to, so these formulas over here is to compute the critic, I mean to train the critic network, computing the loss of the Q function value. And this one is to train the actor, which is using the gradients to maximize the reward. Okay, so as I mentioned, the agent, as other agents have a configuration parameter called experience buffer length. It could be 10,000 experience, and experience is a point that consists of the simulation stop, the reward, and the observation and the action. All that is that set. So basically you have like 10,000 of those, and out of those you select a mini batch, which is size M. It could be 64 or something like that. So what's gonna happen is you take that mini batch and then compute the loss for that mini batch. You can see the sizing here for all those points. So for all of those experiences, you have the observation, the action, and then compute. This is your expected, according to your critic, the expected long-term reward, and you compare it against the actual, pseudo-actual, I will say, long-term reward, which this is the accumulated reward so far in your episode. But also you want to predict the rewards that are going to happen in the future with this parameter is basically to decay the reward. So basically we want the agent to finish as soon as possible, so you decay the reward as time passes by. You get less reward because of this constant. If you set it to 1, then the agent will finish whenever the agent wants. It doesn't matter the time. But in this case, in this type of example, probably you can have a value of 1 because there's no time limit. You don't want the agent to finish fast. You want the agent to keep the car in the lane. So probably you can have a value of 1 for that constant in here. So in here, notice that you're using the target policy and the target critic, and both of them are going to be computed for the future observation, and the action is taken from the policy. So all you have passed is the future observation, the next observation, and that one is going to give you the action and give you the long-term reward. So once you have that, you subtract it and you train the critic like that. And then for training the action, you don't consider the targets. So basically you take the gradient of the critic. You can see it in here, and by gradient it means going the derivative in the direction where the most change happens, and if it is positive, it's the most positive reward. So it's basically where you maximize your reward. That's why you have to use a gradient to maximize the reward, and you maximize the change in the reward, and then with the policy you maximize get the gradient as well, and those two are multiplied and average over the batch size, and then that one you use to update the network parameters of the policy. And again, and once you train at a given cadence that you configure through a parameter, it should be target smooth factor. Well, this is the parameter to update the frequency that should be in the agent. So once you update the target, with this target smooth factor, if it is set to 1, then the target is going to be a copy of the regular network. If you set it to 0.5, then it's going to take half from the regular network and half from the existing target. So it's kind of like fuse them. Yeah. Okay, so let's take a look at the DDPG relative to other agents. So basically this is an off-policy agent. In contrast to the on-policy, the off-policy basically trains the network without the policy, and it's going to have an actor and a critic, you can see in here the DQN only has a value. This is used for the steering, and we're going to use this for acceleration. And the action space, as I mentioned a few times, the DQN is discrete while the DDPG is continuous. And these are the functions that we're going to use for the DDPG. They use RLQ value function, which is the same that is used for DQN. For the actor, we are going to use as I mentioned before, the continuous deterministic actor. And for discrete action space, DQN is not the most basic, but for the discrete, for a continuous, the DDPG is one of the most basic. So there are other examples with more advanced agents. So now let's go back to create those agents. So we're gonna put these functions are part of the example. They are defined in here. They are not shipping MATLAB functions. So we're gonna put a breakpoint in there just to see how they run. So we're gonna pass the observation action info and the sample time. So we're gonna create the acceleration agent. So it's a very basic, fully sequential network with fully connected layers and ReLUs. The feature input layer is gonna be the size of the dimensions. In the case of the steering, it's only 3 elements. You can see it in there, and the output is gonna be the expected long-term reward. But in addition to take the observations, we also have to pass the action. The action is just gonna be a scalar. So the action is gonna be an input. Both of them are gonna be considered, and you can see that there's an addition layer. So the first input is connected to the observation, and the second input, you're gonna see it connected in here. So you can see F5, which is this output, is connected in here. And it's important for the inputs to have a name, observation and action, because once you create the Q value, you have to tell it, okay, this is RLQ value function that I just showed in the agent to create the critic. And you can see that we have the critic in here. So you have to tell the critic the Q value function, which is your observation, which is this one, and which is your action, your input action. So that's how this one is gonna know how gonna feed the action and the input, the observation and the action into the network, the inputs. Okay, so we add the layers. We create a layer graph with this one, and just add the layers for the action path, and then just connect them. And once I have the layer graph ready, I use the DL network to create the actual network. So let's go down there. Okay, now let's take a quick look at the network to see how it looks. The size of the features for the network is gonna be 48. So we can see in here that we have the input of 3. We have a bunch of features of 48. Then we have the action with a scalar, goes to 45. We just add it and get the output. It's just a fully connected layer with scalar with expected reward. And now let's create the Q value function with the observation info, action info, with the deep neural network, and as I mentioned before. Now for the actor, it's a little more simple. You just take the observation, and the output is going to be an action. But the action is going to be an acceleration that goes from -3 meters per second, meter per square seconds, to +2. So basically, we are going to use again fully connected layers with the features of 48 all the way, and eventually we get into a scalar. And the scalar, we use this activation layer that's going to clamp the outputs from -1 to +1. But that's not how the range looks. So we use scaling, and with the scaling and bias, we take the output is going to be from -3 to +2. So that's expected value for the action. So we just have a very simple here, a sequential network, a layers, and so we just use the DL network command on it. And yeah, so if we do this, we can take a quick look at the network. Using analyze network, it's gonna be a sequence with the observation, and the output is the action. Simple. Okay, now we have to get the optimization options for the observation. So we had also in here, so learning rate is gonna be a little bit smaller for the actor than for the critic, and we also have the clamping of the gradient for both of them. Okay, so now that we have the neural networks No, first we create the actor. Given the network and the observation and action info, we have the contiguous deterministic actor. And now we gonna give the agent options. The agent options are gonna wrap into the DDPG agent options. So the experience buffer length is 1 million experience. So it's a bunch of experience from the train that the training is gonna be sampling from, as I mentioned before. So the noise, this is important for exploration, the noise. So you have a variance of noise that is gonna decay. And the reason for this is that at the beginning, the agent knows nothing. So you cannot be greedy, because if you are greedy at the beginning, you're gonna fall into a local minima. So it's more important to have exploration, and this is achieved in this agent through this noise. So it's gonna have a relatively large variance at the beginning to explore, and then as time goes by and as the agent gets smarter, then it's gonna decay at this rate. So you stop exploring as much and start being a little bit more greedy and maximizing the reward. Okay. So finally, you have the options, you have the actor critic, and you create the DPG agent, and we have our acceleration DDPG agent. So let's go and do the same for the critic. For the steering agent. So in here we're gonna have something similar. We have an observation that is gonna take the 6 observations. In here is the lateral error, the yaw rate, and their derivatives and integrals. So it's gonna have 6 elements, and the action is just gonna be another scalar. And the output is gonna be the same. It's a expected long-term reward. So we're gonna have a layer graph. We're gonna add the layers. We're gonna connect the 5 and wrap the layer graph into a DL network, and then have those similar optimization options of learning rate and clamping gradient. So we're just gonna go there, take a quick look at the network. The number of filters, the number of features per layer is smaller, it's 24 rather than 48, as in the case of the acceleration agent, but it's the same concept. Basically, very simple network. So now we have the critic network, we have observation info, action info. We again have to communicate the observation and the action so that they can be fed into the network. So we have our critic. The agent options are basically, we're going to use a double DQN like in the last example. And we have the experience buffer of 1 million as well, past the critic options. And so we have the agent options and the critic network and the actual critic that we created with the Q-value function, and that's it for a DQN agent for the steering. So now we have the agent for the acceleration, and we have the agent for the steering. And if you go back at the model, you're gonna see that if you do Control D, now it's not running anymore. Still, the final time that is used here is not defined. That's why it's complaining. So let's go back to the model. Now we have the agent. We're gonna specify the training options, and the final sample time is gonna be 60 iterations. So we go back to the model, and you should not get any errors right now. Yeah, it compiled without errors because we have everything defined. So let's go back to the desktop, and so we have 60 maximum iteration. Maximum episodes are going to be 5,000, but this is going to converge way before than that. I think 140 episodes. So we're going to have a total of 600 max steps per episodes, and we passed that. We just plot the progress, no verbosity. And notice that everything, now that we're training 2 agents at the same time, everything is in pair. So when we specify the average reward to stop training the 2 agents, we're going to specify first that the acceleration agent is going to stop when the reward is 480, and the second agent is going to stop when the reward is 1195. So again, so that's in the options, and also in the training we have to pass the agents in the same order: agent 1, agent 2, plus the training options and the environment. So that will start the training, and I'm not gonna run the whole training because it takes a lot of time, but at least I'm gonna launch it. One interesting thing is to see how the agents start to behave at the beginning of the training. So you're gonna see it in a moment, and you can see in here, whoops. Okay, you can see the training in progress in here. So the blue is the relative distance and the safe distance is yellow. So in here the velocity of the lead car is red and the ego car is blue. So you can see that the velocity doesn't get anywhere near the velocity where it has to go. And yeah, regarding the error, it's out of zoom. I mean, a little bit of zoom will help this, but the point is that it begins far away from the goal. You can see the steering is behaving well, so it seems that the steering is close to zero. It gets adapted faster than the acceleration. So this is taking more time to get to a safe distance and actually match the velocity. In here you can see that it's behaving a little bit better. So you can see in the progress in here, so far we have been 5 minutes and the average reward is still negative. So both of them are not having yet a good reward. This one is getting a good reward, as you can see. It's getting closer. So as it's consistent with what you see there, that the lane, the car is getting stabilized in the lane, but still the acceleration and the safe distance is not getting there yet. So it's gonna take a time. So this takes a total of about maybe 1 hour and a half to train. So I'm gonna stop it and I'm just gonna load the train model from the example. Okay, back in the desktop, we're gonna load the agent rather than train it. Okay, so I just load the agent. It's gonna take a while. So we're gonna try to see if it simulates correctly. So we're gonna use the sim command from the environment and get the experience, and we're gonna see how good it goes for both the acceleration and the steering, and then we're gonna see the simulation in action. Okay, so it's gonna take me. Okay, so first we get the simulation options, which is basically the number of steps that we're gonna use is 600. So now we're just gonna run this. I don't know what's happening with my mouse today, but anyway, I'm just gonna use the cursor. So this is actually a method from the environment. So we just, again, for the simulation, we have to pass the agents in order: first agent, second agent, and the options. And with that, we get the experiences. It's gonna take a while, so I'm gonna pause. So in here we're gonna have two structures because we have two agents. So let's take the first agent. Start the first agent, and you can see that it has a reward, and from the reward we have the data. And you can see that the reward is 1 at the end, but at the beginning it is quite bad. So let's plot it. So we're gonna see in the plot, oops, yeah, here's the plot, and you can see for the acceleration it starts bad, but eventually gets to the good reward, which is what we want. And then for the second one, let's take the second one is for the steering. Let's see how the steering behaves. And you can see that steering it gets to the maximum, the saturating reward, the maximum reward earlier than the accelerator. The acceleration problem is a little bit harder. So now we're gonna see the simulation of this control of the acceleration and the steering in the actual simulating model with the plots. And first we have to initialize the environment. The initial lateral error, the initial yaw relative angle, and also the position of the car in the front. So I know that the safe distance is about 50 or something like that. So instead of having 80, I'm gonna put distance below the safe distance, so that the car has to do adjustments to get at the safe distance. So in terms of the lateral error, we know that if it goes, the absolute value goes above 1, game is over. So let's just put something close to the limit. And then the angle goes from negative 0.5 to negative 0.5 to 0.5. So let's put 0.4 radians. So everything is close to the limit. So let's make it real hard for the environment to adapt, and let's see how it behaves. Okay. And now we can use the sim command, but instead of doing that, we're just gonna run the model. So we're just gonna use this one. So I'm gonna put the plots just to show it. I had to change these parameters a little bit because the model was not working. So instead of having something close to 1 to the maximum lateral deviation, I changed it to 0.5, which is halfway. And also the initial, I drop it down. Instead of going too close to the limits, I put somewhat halfway. And also the lead distance, I put it to 20. So I basically changed that in here. Let's go back to the simulation, and now let's run it from the beginning. And you can see that the blue one is the ego vehicle. At the beginning is far away from the velocity, but eventually it gets to this place. At the beginning, the velocity of the lead car, the car in front, is red, is lower, so it's gonna follow the lead car. But when it gets here, that the lead car velocity goes above the desired velocity, then it takes the minimum, as we saw in the blocks. So it follows this velocity, but then the lead car accelerates, and then it follows the lead car again. So this is what we saw inside of the dynamics of the ego car. And for the reward, that's for the reward, my bad. For the acceleration in the reward, we saw that. For the case of the safe distance, we start at 10 or something. It should be something like 20. But anyway, it's gonna increase the safe distance. It's gonna increase the distance between the ego car and the lead car, and eventually, when it gets to this point, is at the desired safe distance. But then it gets more than that. So the agent doesn't it's not necessarily have to be at the safe distance, it just have to be higher than that, so it goes a better distance. For the case of the steering, it is easier than the acceleration, and keeping the distance is basically, it keeps the car in the lateral error. It doesn't go outside of the lane, and you can see it close to 0 very fast. And the same goes for the angle of the car. So the angle of the car starts very crazy, as you can see in here, and eventually it gets to 0. So if I put something with a weird angle and almost close to the boundary, of course the car is gonna go out of bounds easy. So the simulation is gonna stop. That's why I was not getting such a numbers. It's like putting the car almost about to go outside of the lane. Okay, so this is it for the video. Thank you very much.